Good morning, students. Today we shall discuss multivibrators as given in your syllabus. At the beginning, I want to share something with you. There used to be transistor-based multivibrators maybe 5 or 6 decades back, 50 to 60 years. And in my view, it is not at all necessary for you to learn those transistor-based multivibrators. Basically, what are multivibrators? It creates pulses. Now, in various form, various shape, various time period, pulse period, etc., etc. And 50 to 60 years back, there used to be transistor-based, BJT-based multivibrators or FET-based multivibrators. And I don't think there is no use of learning those multivibrators now. Presently, any pulse generator, you call it a multivibrator or monostable, whatever it is, any pulse generator is made out of standard timer circuits. And famous and very popular IC is 555. You see here 555. There are, depending upon the company which produces it, it can be any 555, it can be LM555, anything, but it is 555. It is very popular and very often used. And also cost is nowadays very low cost IC. Nowadays, all the pulse generators or pulse related circuits, I would say 99% of them are assembled out of this timer circuit. So this timer circuit has 8 terminals. There is a terminal VCC where the DC voltage is connected. Depending this, and if you have to go to the manual of the circuit, manual of this particular type of timer that you have taken, normally this range of VCC is 5 volt to 15. If you take 5 volt, then your pulses will be 5 volt height. If you take 10 volt, it will be 10 volt height. There is a ground terminal and there is output terminal. These three are very clear. There are 5 other terminals. One is reset terminal. Another is discharge, DIS, discharge terminal. Another is threshold terminal. Another is trigger terminal. Another is control terminal. These are the 5 terminals you need to learn how they are to be connected. Connection of VCC, output and ground is everybody knows how to do it. And I have also shown the ground connection, VCC connection, output connection. I have used the output load RL for the sake of circuit completeness. Okay. Now let us see how these 5 terminals are to be connected. This control terminal is used only in very special cases. When you see the IC manual or your textbook, you will find in some very special circuits, the control terminals are used. And in your syllabus, you have only monostable, astable, monostable, and astable. So you don't need control terminal there. And when you do not connect control terminal, then you connect a filter capacitor of 10 nanofarad, very small capacitor to common, from common to control terminal. In fact, I have seen if you do not even connect it, it works. But for safety of the IC, you should connect this capacitor. So this capacitor also you take out of your mind. What we are left with then, these 4 terminals. For monostable astable operation, reset terminal is connected to VCC. In fact, when the timer is running, if you have any special application when you have to reset this, then you have to connect the reset to common. But for this application, you do not need reset, so keep it permanently connected to VCC. Now, these are the two components, R and C, which determines the pulse duration, right? One end of R is connected to the VCC, other end of R is connected to discharge. And discharge and threshold terminal are short-circuited because we are discussing monostable connection. Monostable is, I might have not told you already, monostable is, and this is a pulse, this is a, I should say, signal generator which creates narrow pulses. I'll show you first this function of this signal generator. This signal generator, you know, this red pulses, signal generator creates this negative going small short pulses. So these are the triggers actually. So this signal generator goes to the trigger, or signal generator creates the trigger pulses, right? And trigger pulse is normally high. It is at 5 volt, and then when a trigger is to be given, it comes to 0. And the trigger pulse is always very short. I have just taken a few microseconds, about 100 microseconds. This is the trigger pulse. Okay. Now, what is a monostable? Monostable is when there is a trigger pulse, then here actually I have kept them separate for you to see it properly. If I adjust the oscilloscope to bring them in the same horizontal line, it's like this. This is where the trigger pulse occurs. When the trigger pulse occurs, the output goes high. Right? Again, next time trigger pulse occurs, output goes high. And output will become low after a certain time, which is the pulse period Tp, which is equal to 1.1 Rc. R is 1K, C is 270 nanofarad I have taken. You can choose anything. If you make 1.1 Rc calculation, it is 300 milliseconds. So I make them, separate them once again for you to understand it clearly. Right. So the idea of the monostable is when the normally output of the circuit is low, and when there is a trigger pulse, and trigger pulse is always the negative going edge of the pulse, then output becomes high. And after a certain time determined by 1.1 R and C, the output by itself becomes low again. It does not depend upon removal of trigger. You just give a trigger and forget it. Output will go high, and after this particular time, the output will become low. That means here the circuit is, now if we see the circuit, see the operation, see this is the operation. So each negative going edge of the trigger, the output goes high. And then after a certain period of time, output becomes low. It does not depend upon trigger anymore. Next time, when once again there is a negative edge of the trigger, output goes high. That means here, this circuit is stable only at low output. That means output 0. And when the output is high, it is not stable because after some time it goes down again. And that is why it is called monostable. If you see your IC manual, you will find the same 555 timer. You can connect it as other way around. That means output is normally high, and when there is a negative trigger, output becomes low. Right? That also is possible. So this is a monostable. Now, in your textbook, you will find there are descriptions of what is inside this 555 timer and how it works and As a teacher, I feel that is not necessary for you to learn because you are not going to design a timer anytime in your life, right? So you have to always use a timer. So instead of wasting your time, what is there inside this timer IC, rather you in your college laboratory or at your home with a software simulation, you learn all numerous applications of the timer circuit. Numerous applications are given in your textbook. Just keep on simulating them and see how it works, right? And in your practical service life also, you will have to only know how to apply it, what should be the connection so that it works in your desired fashion. So this is your monostable time. Now we'll go to astable operation. This is a astable operation. Astable means it is not stable either at low or at high. Output is not stable. So, and it does not need any trigger also. Astable means it keeps on going to from low to high, again from high to low, again from low to high. It keeps on going. It is not stable anywhere. And actually, it creates a series of pulses which are you can say the basic source of any digital circuit, and that is why the 555 timer, monostable, astable, these are very important for you to know how to use them, right? You will be always using the timer as a source of your digital circuit, right? So here you will find output VCC and ground connection is same. Control connection 10 nanofarad capacitor is same. The trigger is connected through a capacitor C. It remains same. Earlier also it was connected to a capacitor, right? And see, earlier the trigger was connected to a trigger source. Now trigger is connected through this capacitor here, and trigger and threshold terminals are shorted, and there is a resistance RB between the discharge and the threshold trigger terminal, and this resistor RA as usual between the discharge and the power supply VCC. Here, for a certain duration of time, the output is high. That is when the capacitor is charged through this line, right? Capacitor is charged through this line through RA and RB. So charging time of RA is RA plus RB into C. And if you go for detailed calculation, which once again I propose it not necessary, the charging time is 0.69 RA plus RB into this capacitor. And for the values that I have taken here, this charging time is 421 milliseconds, right? And when the capacitor discharges, it discharges only through RB, right? Through RB, it discharges through this discharge terminal. This is a discharge terminal. So discharge time constant is RB into C, 0.69 RBC. And with these values, it is 269 milliseconds. So total period is 0.69 RA plus 2 RBC. It is, if you add these two, it is 0.69 millisecond. So the high pulse time will be 0.421 millisecond, and pulse stop time, that means zero time, will be 0.269 millisecond, and total pulse period will be 0.69 millisecond. And there is a term called duty cycle. Duty cycle of any pulse train always means the ratio of pulse on time divided by total period. That means it will be TC by total time, which is equal to RA plus RB divided by RA plus 2RB. And with these values, the duty cycle is 61%. So this is how Astable is connected, right? Now I shall show you how I shall show you the running of the astable. I shall make it run and then I shall reverse the display. See, the astable is running. I shall stop it and show you. So charging time is this on time. This is from here, and that means this is the period when charging time is on, right? And it is showing here 416.667 microsecond, microsecond. So this is, that means 0.416 millisecond. So this is approximately 0.421 millisecond, right? And discharging time, it shows the off period of the pulse. That is the off period of the pulse. It shows 0.27 millisecond. Here it is 0.269 millisecond by calculation. And so total period of the pulse is, which shows total period of the pulse shows 600.691 millisecond. Total period of the pulse is 69 millisecond. Anyway, so I run it once again. This is how the astable multivibrator works, right? The pulse keeps on going up and down. That means this is the source of digital pulses, which is very, very, very commonly used in your digital electronic circuit laboratory. Now, here you see the pulse period on period 421 millisecond, pulse off period is 469 millisecond. They are different values. And duty cycle is 61%. If I want to make duty cycle, and in your digital circuit, you need a pulse strain of 50%. And those pulses are called square wave pulses. That means on time and off time should be same. Now here, by proper selection of RA, RB, and C, we can make duty cycle 50%. And if we can make it, that will become a square wave generator. So square wave generator. Now look at this. This is the charging time and this is the discharging time. Charging time is RA plus RBC, discharging is RBC. And if you want to make them both equal, then RA plus RB should be equal to RB. That means your RA should be 0. This RA should be 0. But if RA is 0, then the circuit does not work. What do we do? Some people have found out an excellent idea. You see, it is the same circuit here, only across RB, there is a diode connected. So, when the capacitor is charged, it's charged through RA and the diode. So, charging time is RAC. And when it discharges, discharge current does not flow through the diode because it is then reverse biased. Discharge current is through RB, and that means discharge is RBC. Discharge is RBC. Now, if that means it is possible now, if you make RA and RB both same, then it is possible to have a square wave pulse and duty cycle will be 50%. Now, here in my circuit, I have taken RB as 4.7 kilo ohm. Here also I can connect a 4.7 kilo ohm resistor, but every resistor has a tolerance. In your laboratory, if you use a resistor, you will find duty cycle is not exactly 50%. So what normally we ask our students that connect a potentiometer here so that you can adjust the potentiometer here to exact value, right? So here you can see I run this circuit now. I run this circuit now. It is running. Now let me see what is the duty cycle. Let me check, measure them. This is the, if I take this from here to here, this is the off period of the pulse. Off period of the pulse is 340 microsecond, 340.9, that means 341 microsecond. And on period of the pulse is 369 micros, a slight difference. So this difference in your laboratory, you can always adjust by adjusting this potentiometer. So this is here. I'll show you this for simulation. This is P is A. So see, if it is running, it will not work. If I make change A from, it was 60%, now I have made it 40%. You see now on time is larger. So let us reduce it. Let's make it 65% now, potentiometer. Now I think the on time and off time has become same. So what you have to do, you have to use a potentiometer here. You can always use in your laboratory, you will find multi-turn potentiometers, which are very accurate potentiometers. And by using that potentiometer, you can use that a square wave generator, because this circuit will be very useful for you when you are doing your college third year or fourth year project, because in your projects very often you need to create a square wave generator, and with the help of this circuit you can easily create the square wave generator that you want. And the total time period is 0.69 Ra plus RBC, and frequency is reciprocal of the time period. So you first decide what is your frequency you want. You want a 1 kilohertz pulse or you want a 1 megahertz pulse. Accordingly, you decide Ra plus RBC. Then you decide any value of C. Then you have Ra plus RB, and half of Ra plus RB, one half should be here, one half should be here. So it is very simple to design this astable multivibrators. So here we shall end the topic of multivibrators. Once again, I tell you, I have purposefully have not taken you into the domain of old days BJT-based multivibrators. They are absolutely obsolete now. You cannot get it anywhere. There is no use of those circuits now. Okay. Now, next day we shall go to the next subject. Today we finish it here. Okay.